Good afternoon, everyone. So thank you all for coming along to this Royal Meteorological Society webinar on weather and climate hazards, impact forecasting and modelling insights in the insurance sector. We'll get started in just a moment. We've got a few brief things of kind of housekeeping to get started with though before we start. So obviously this meeting is being hosted on Zoom. The main feature of this webinar is that all questions and chat will be done via the Q&A in the chat at the bottom of your screen. So when we get onto all of the different speakers, you'll be able to insert your questions into the Q&A, and all of the questions you'll be able to, if you think it's a good question, give a little thumbs up to, and that way we can see kind of the most popular questions that are coming out and we can pick to address to our speakers. So before we get started, just a quick bit of information on the Royal Meteorological Society. So the Society is the UK's professional and learned society for weather and climate. And what we're doing here is trying to raise awareness and engage people with the weather and climate science that's being done around the world and support people working in meteorological professions. And also the purpose of the Society is not just to benefit those who are operational meteorologists, but all those with a broader interest in meteorology and weather and climate science as well. So as a result of that, the Society set up a number of special interest groups just over a year ago, one of which was the Insurers Special Interest Group, which is who's hosting this webinar that we're attending today. So the purpose of the Insurance Special Interest Group is to engage those in the insurance and financial sectors doing weather and climate research with academics and others doing research relevant to them. So as part of the group, we have 20 academic and industry professionals who meet every 3 to 4 months to discuss content that we can produce to address the meteorological and climate needs of people in the insurance sector and academics. We have discussions on future research directions, highlight career opportunities, and kind of just pave ways for kind of research development in the future. So as a result of this, we've put on this webinar today where we really want to highlight some of the really exciting research done that's relevant to the insurance sector, done both by academics and by those in the insurance sector. So as a way of an introduction, there's going to be 2 of us from the Special Interest Group hosting this meeting today. So I'm Matthew Priestley. I'm the Science Engagement Fellow for the insurance sector with the Royal Meteorological Society. I'm also based at the University of Exeter, where I'm a postdoctoral researcher working on European storms. And joining me today to help out with this webinar and co-chair is Katie Latham from Willis Towers Watson. So Katie, if you just want to give a bit of an introduction to yourself.
Yeah, sure. Thanks, Matt. So yeah, Katie Latham. I work at WTW or Willis Towers Watson, where I lead the natural catastrophe analytics team within the global markets, direct and FAC insurance placement teams. So really that means supporting our brokers with the large and complex like placements and being able to provide the context of the risk that they are placing, and of course that includes many meteorological risks. My background is in meteorology. I worked for 4 years at the UK Met Office before I joined WTW about 6 years ago now, yeah, my educational background is in meteorology as well.
Great, thanks, Katie. So as part of this webinar, you'll see on the advert, we have 3 great speakers lined up who will each give a talk for us now. So we have Sandra Hansen, James Dunn, and Sem Vijverberg. And so I'd kind of just like to invite all the 3 of the speakers to give a brief introduction to themselves first. So Sandra, if you want to just give a quick introduction to yourself and what you do.
Yep, thanks, Matt. So my name's Sandra Hansen. I work for Guy Carpenter in London. So we're a reinsurance broker. We help our clients manage risk. I lead our international peril advisory team. So we aim to provide sort of a bridge between research and the insurance industry by collaborating with data providers and academic institutions to enhance our insight into natural catastrophes from an insurance perspective. And we cover all regions in Europe, Asia Pacific, Middle East and Africa. I have a background as an actuary as well as a mathematician and as a meteorologist prior to Guy Carpenter.
Great, thanks, Sandra. And yeah, next up we have James Dunn.
Yeah, hi everyone. Great to be here. Thanks for the invitation to speak today. Yeah, I'm James Doan at the National Center for Atmospheric Research here in Boulder, Colorado. So I study high impact weather in a changing climate. I'm also a Willis senior academic, so I've been working with WTW for a long time now, conducting collaborative work in the field of hurricane risk. So I'll say a bit about that today. I also want to take the opportunity to thank the Society, because I was fortunate to be a recipient of an early career Rupert Ford Travel Award about 20 years ago, and that brought me to the US, and I've been here ever since. So I'm very fortunate for the support they've given me over the years, so thank you.
Great, thanks, James. And finally, Sam, if you could just give a brief introduction as well, please.
Yes, thanks, Matthew. Yeah, nice story, James. Unfortunately, I don't have one yet, but like that. I'm Sam. I have a background in climate physics, and I have done my PhD at the Vrije Universiteit, focusing on applying machine learning techniques to make weather predictions weeks up to months in advance. Yeah, and I will talk a bit about that later.
Great, thanks, Sam. So yeah, as I said, each of the three speakers here is going to give us a approximately 15-minute presentation, after which there'll be opportunity for questions after each one, and then for the final 20 minutes or so of the hour-and-a-half slot we have, we're going to have a kind of more general, open, broad discussion. So as I said at the start, any questions that you have throughout for any of the speakers, either from their talks or for the discussion at the end, please pop in the Q&A section you'll see at the bottom. And as I said, if you find a question interesting, give it a little thumbs up and that'll bring that to our attention. So I suppose to get the ball rolling, we're going to have Sandra first from Guy Carpenter. So yeah, Sandra's going to talk to us about some of the windstorm research that she's been doing. And yeah, away you go, Sandra.
Thanks very much, Matt. So today I wanted to focus on European windstorm and how we can use seasonal forecasts to enhance our understanding of extreme storms. Firstly, I wanted to mention this was a collaboration project with the University of Exeter. So Jacob Madison at Exeter did the majority of the research with supervision by Jennifer Cato. So yeah, I should thank them a lot for all the work that they did on this collaboration project. Firstly, I wanted to explain the motivation behind this research project, then talk a little bit about how we carried it out. Then we validated the output, and then how we used the resulting events. And then just to summarize on the key conclusions from that. So I wanted to start with talking about evaluating catastrophe models, because this is something that we do a lot of in our team. So why do we need to evaluate CAT models? Well, I mean, there's three main reasons. The first one is reinsurance pricing. So we help insurers purchase reinsurance. And to do that, we need to have a good idea of what we think is a fair price. And that requires some knowledge of the peril and of the models. And we also may want to adjust the models. So we need to be able to justify those adjustments. Secondly, insurers may use models for their internal capital models, and so they need to have a really detailed understanding of the models and be able to document that and submit that to the regulator. And then finally, just for internal risk management purposes, understanding the risk and where to write further risks and how to manage existing risks. So MSA is model suitability analysis. That's our framework for evaluating models. And the idea is, with this MSA framework, that you own your view of risk, you're able to understand and quantify and qualitatively explain the models. And this is all supported by credible data and science. We have three main components that we look at. So the first one is sensitivity testing. And this is around how changing exposure assumptions can impact the modeled loss. And this can be useful for understanding how a model performs, understanding where to collect data on our exposure, and where to write further risks. Secondly, we have a component on loss validation, and we can use that to look at modeled losses compared to actual experience. And finally, scientific benchmarking. And this is one of the areas I'm going to talk about today. This is around how we look at the different components of the model, for example, hazard or vulnerability, and comparing those components to science, data, references, to come up with a credible view of how that part of the model performs. So if we, for today, focus on the scientific benchmarking part and focus on how we can validate the hazard. So as I said, we're talking about European windstorm today, but there's lots of data out there that we could use. We could use reanalysis, we could use station observations. So why do we need another reference data set? Well, I mean, the data may either cover only a short time period, or it may not be of very high quality. One project that we looked at some years ago was using geostrophic wind data from a research paper by Kruger and Wang. And they were looking at geostrophic wind speeds over pressure triangles in the UK and Ireland. And we used that with an appropriate threshold to define a storm, and therefore to count the storm activity in each year from 1902 to 2016. And that's where you can see in these red bars, this is the annual storm frequency in the UK and Ireland. And the black line is the 10-year rolling mean. And the point of this really is to show the variability in windstorm activity. And you can see the quieter period in the 50s and 60s, and the more stormy period in the late 80s and the early 90s. And this is important because a model is typically calibrated to a certain historic period of time. And this area that I've circled, this is a typical model calibration period. And as you can see, that was quite a stormy period in the UK. But is that a fair reflection of windstorm activity today or over the long term? Possibly not. So the actual calibration period you choose can have quite a big effect on your assessment of storm activity. And the observational data that we typically use, station observations or reanalysis, is often only available for quite a short period. And further than that, if you're looking at a measure of storm intensity, for example, the Storm Severity Index, and I'll explain a bit more about that in a minute, but it's basically a way to represent storm severity. You could look at academic studies, but these might not use the same definition of Storm Severity Index that we might use in CAT models. So the goal of this project really was to provide an extended event set. So we had 672 years of data and 85,000 events. And with that, we can improve our understanding of catastrophes, and also do that in a way that's consistent with the measures that we use in the insurance industry. So to briefly explain how we did this. So as I said, this was a collaboration project between us, Guy Carpenter, and the University of Exeter. We looked at Met Office seasonal forecasts, seasonal forecast model, and we did this at 4 different initiation dates, and for 24 years each, and for 7 ensemble members. So we ended up with a large ensemble of different model runs. We then used the Hodges algorithm to track the storms in that data set using sea level pressure fields. And then we calculated the Storm Severity Index, and we used this definition that's consistent with what we typically see in the insurance industry. Finally, we had to do some bias correction to convert wind speed to gust. So the Met Office seasonal forecast model, this glossy 6 model, does not contain gust data, only wind speed data. And so we had to do some conversion to make it more appropriate using a gust. And in the end, we ended up with 672 years of events, and this was including tracks, footprints, Storm Severity Index, and a lot of information that's really useful. And I'll come on to the types of things that we could use it for and that we did use it for. Just wanted to explain a little bit more about the bias correction. So firstly, the Storm Severity Index that we often use here in this industry incorporates the wind speed intensity, but also the size of the storm. So it encapsulates the intensity of the wind speeds, but also the area covered by the footprint. And it's normalized by the area of the country. So the first bias correction we did was on the threshold. So the threshold in the storm severity index is typically 20 meters per second for a gust. And we consider anything above that to be damaging in general. So we calculated that gust threshold in ERA 5 in the reanalysis data and the equivalent percentile. And then we could then apply that percentile to the seasonal forecasts, the Glossy 6 runs, to come up with an equivalent threshold for wind speed. As I said, we don't have the gusts, so we can't use 20 meters per second. We have to use this ERA 5 percentile to come up with a more appropriate threshold. We then calculated the SSIs in ERA 5 and in Glossy 6, and we used the gust SSIs and the wind speed SSIs in ERA 5 to come up with a bias correction and applied that to the Glossy 6 wind speed SSIs in order to convert that to a gust SSI. So in terms of the validation of this, so on the left panel, you can see the track density, the storm track density over Europe. In the top here, you've got the ERA 5 reanalysis, and then in the middle, you've got the Glossy seasonal forecast. And you can see that there's a reasonably good representation of the storm track. You've got peaks in track density in similar regions. There are biases, and as there probably would be in most models, but overall, it's reasonably well represented. Again, in the middle, you've got the intensity, the mean intensity, and that's also reasonably well represented in the seasonal forecast. And on the right, you've got the 10-meter wind speed. There is a slight overestimation of wind speeds for some countries, but in general, it seems to perform reasonably well. Here we're looking at the storm severity index now, and the distribution of that storm severity index for all the different countries. You've got ERA 5, the reanalysis in black, and the Glossy seasonal forecast in purple. And what we wanted to see was that there is a reasonable match in that the seasonal forecast has sort of similar peaks and has a reasonable representation of storm severity index distribution. We don't expect them to exactly match because that's the additional value we're getting from the Glossy model, is we don't want it to be exactly the same as ERA 5. But generally speaking, we saw reasonable agreement between the two. There are some regions, for example, mountainous countries, where there's a bit more of a disagreement, and that could be related in part to the bias correction that we had to do. But what is interesting particularly is what happens in the tail. Does the Glossy forecast produce more severe events than we've seen in the reanalysis? So this slide is looking at the same distribution, but just in a different way. So in this case, we have a box plot of the SSIs for each country. And what you can see is that the Glossy, the seasonal forecast, it produces higher SSI values. So it produces more extreme storms than what we've observed in the reanalysis. And that's what we wanted. We wanted to be able to get an understanding of the tail events. Other than that, the distributions are, as they would be different, but we do see reasonable agreement in the general, in the body of the distribution. So coming on to how we can use this data and what we have used it for. So as I mentioned, we have 672 years of roughly 85,000 events. So it's quite a large event set. So we could look at the frequency intensity distribution, and I'll explain that particular use case in more detail in a minute. And that this is an important metric for model evaluation. We could look at clustering, and again, this is the second example I'll show in more detail, but how is windstorm clustering represented in the model? So by clustering, we mean storms arriving closely together in time and space. Other things we have used for as well are cross-country correlation, so understanding how windstorm activity is correlated between different countries in Europe. Understanding the seasonality of windstorms, other characteristics of extreme storms. And finally, eventually you could use this event set to build a model or to develop a risk score. So to explain the first use case in a bit more detail, this is one thing you can look at in the catastrophe model is the distribution of the storm severity index by return period. And here I show in black the reanalysis. And this is the actual historic points are in the black dots, and then we can extrapolate that with different thresholds to come up with a range. The yellow here is the seasonal forecasts from the glossy model. And what we've done is we've subsampled the events. So we've taken 50 years and done that 20 times to come up with a range of outcomes. And those are the yellow lines, and then you've got the crosses. These are the additional return periods, the additional storms that we wouldn't have seen in the reanalysis data. We did an additional bias correction step to bring the two data sets in line at a 10-year return period. And this was where we have a large amount of observational data. We can say that they should probably agree. But what the seasonal forecasts do is they give us some information about these longer return periods that the reanalysis data doesn't. But we generally found that the two data sets agree quite well. And this is for the Netherlands as an example, but we can do this for every country in Europe. And we can see that it's slightly flatter in the tail than the reanalysis extrapolation. We did the same for the UK, and in this case, we can see that to a greater extent. We can see the seasonal forecast tail SSI values flattening out a bit faster than the reanalysis extrapolation. But the value is in providing additional views to help us understand the potential tail risk and extreme storms. And then just to mention that this agreement worked quite well in most countries, but not as well in some mountainous areas. But really the value is in these additional return periods for a majority of countries. And then the last case study is on clustering. So as I mentioned, clustering, the windstorms occurring closely together in time or space, that can increase aggregate losses. And storm severity index is quite well correlated with loss. So as a proxy for the impact on the aggregate loss, we can look at the impact on the aggregate SSI. So we sum the SSI values in each year. We do that in the seasonal forecasts, but then we can also redistribute the events and look at and recalculate the metrics. So this is a randomized distribution of events in the years. And that can give us a ratio of a clustered aggregate SSI versus an unclustered aggregate SSI. And that's what the black line represents in the seasonal forecast model. And then again, we have subsampled that model, those events. We've done 10 samples of 100 years to create a range of clustering outcomes. And you can see that at the medium to long return periods, clustering could increase aggregate losses by up to around 20%. And this was an example for Germany. We compared that to a study by Matt Priestley, who's hosting this session on clustering, and found, and this was based on a different set of model simulations, global climate model data, and we found that reasonable good agreement with this study, showing a similar clustering impact of up to around 20% at 200 years. So just to summarize, we need reference data sets to evaluate catastrophe models as a scientific benchmark. The typical references we might have might cover only a short historical period and might not use a consistent metric to what we typically use in the insurance industry. Through this collaboration project with the University of Exeter, we created this extended set of 672 years, many tracks, and this is derived from seasonal forecasts. The glossy seasonal forecast model we found was suitable for this approach to estimate risk from extreme storms. And the event set could be useful for a number of different applications. For example, extreme storm characteristics and clustering. And what we found is more extreme storms in this seasonal forecast data than what we found from reanalysis and observations. And that can enhance our understanding of these extreme storms that occur at higher return periods.
Great, thank you, Sandra. That was really, really interesting. Just a reminder to everyone that if you have any questions for Sandra, to please put them in the Q&A section of the chat at the bottom, and then we can put those to her. So just quickly to get started off, I suppose, you showed in some of your return period plots that your SSI values seem to flatten off almost when you got to very high return periods. And is this anything to do with using ensembles in your analysis? For example, do your high return period years, are they all ensemble members from the same simulated year, for example? Have you looked at all into what years they're coming from, your high SSI events?
Yeah, I mean, I think it might be to do with the period that we ran. So the 1994, I think, to, I'm not sure it's here, 1994 to 2013, I think it was. It's because it's quite each run is only 215 days. It doesn't drift too much from the climate, the historic climate. So it may just be that it's not, unlike a climate model, which might drift more and produce some more extreme storms that we haven't seen, it might not be doing that as well. And then there's also considerations around the bias correction that we used. We did that at a country level. So we had to convert, for a start, we had to convert the threshold and also the actual wind speed SSI. So there's some approximations involved there.
Great. And one of the questions we've had in the chat from the from the attendees as well, so from Jonathan Lister, he asks if you've looked at historic records at all. I assume for your extreme wind events, maybe this is relating glossy, what you see in glossy to the extremes that you see in observations.
Yeah, I mean, so we sort of treat reanalysis as history, and so we did that comparison. We haven't looked at station observations, for example, in this context. We do look at them, but we haven't yet analysed them in comparison to the glossy runs. Okay, great. In the interest of time, we'll move on to the next speaker, but thank you, Sandra, again. That was really great. So yeah, Katie will introduce the next speaker.
Right, yeah, great. Thank you, Sandra. Thank you, Matt. Yeah, really interesting presentation there. And so yes, now we'll move on to James, who's going to talk to us about tropical cyclones.
Great, thanks, Katie. Yes, so we're going to move from European windstorm to tropical cyclones now. Yeah, so this is a project that was conducted in collaboration with WTW, where we were interested in developing a new view of inland hurricane winds. So get started. So the main messages today. So we mapped the behavior of inland tropical cyclone surface winds, and we did it globally. And to do so, we developed a new process-based model of tropical cyclone winds. So we wanted to capture the essential physics of how hurricane winds behave in regions of complex coastal terrain. And the information was broadly scientifically relevant and also relevant to the insurance industry. And that was made possible because of this collaboration between public science and the reinsurance sector. And the work I'm presenting today was published 3 years ago now in this paper listed below. Okay, so I'll start with some motivation. We really have a lack of understanding of how tropical cyclone winds behave inland, particularly in regions of complex terrain, and there's not much data. So using the example of Hurricane Otis, I'm sure we're all familiar with images such as the one on the left. So Otis's Category 5 winds really devastated Acapulco about a month ago now. But then one question is how far did these damaging winds extend, either along the coast or inland? Because if you try to search for wind data for Hurricane Otis in the public domain, we often just get the track data. So that's one value of the maximum wind speed per time. But how are these winds distributed spatially? So that was the question we asked. Some more motivation. This was a nice study about 10 years ago of Hurricane Fabian in 2003 that passed over Bermuda. So here's a map of a part of Bermuda, and the black dots are where roofs suffered damage, and the shading is terrain height. And we can see that the location of the damaged roofs preferentially located in high terrain. And this terrain is really quite small, only up to 80 meters elevation height there, but it clearly has a big impact on damage. And this paper further went on to show that even these small terrain features can have outsized influence on winds. So this is a map of Bermuda again, and they took a smooth analysis of the surface winds of Hurricane Fabian and then coupled that to a linear boundary layer model to look at how changes in surface roughness and elevation can change the hurricane winds. And we can see along these ridge lines, the winds increase by 50% or more. So clearly we want to include some of these effects in our understanding of inland tropical cyclone winds. So we have a number of choices of how we may want to model tropical cyclone wind footprints. So let me just run through some of the choices, and I'm sure there's many more I haven't thought of here. But one of the most common is these parametric radial wind profile models. So this is a function that says how the wind speed varies from the eye of the hurricane to an outer radius. And these models are very fast to compute, but they generally produce smooth wind fields. And you often need to apply factors to account for various modulators of the wind. A second choice is a spatial analysis of observations. So many of us will be familiar with the H-Wind product. So these are nice when we have a lot of data, such as from ocean buoys or inland surface station observations. But it's rare globally that we have such dense observations to produce one of these spatial maps. Another choice is spatial statistics. So we can learn from historical footprints and use a model that learns on the historical footprints to produce new footprints. This is, I think, mostly been applied to European windstorm so far. I think a few people have explored it for tropical cyclones, so I think this is a growing area. And then finally, we have full-blown numerical modeling. So you can simulate landfalling hurricanes with a numerical prediction model. So of course, this includes many physical processes, but computationally expensive, and sometimes the simulated track can deviate from the observed track, which is a problem if you want to relate surface winds to damage. So what did we do then? Well, we wanted to retain the essential physics, but maintain fast computational speed. So let me walk you through what our approach is. So first off, we take TT track data. So this could be historical tracks from the National Hurricane Center or IB tracks, or even from global climate models. And then we do run a parametric wind profile along the tracks. So we explored Willoughby or Holland models as choices. And then we use that wind field to drive a numerical model of the lowest 2 kilometers of the atmospheric flow. And we use the Keperton-Wang numerical boundary layer model to do this. So the advantages here, we retain fast simulation, and it includes the effects of terrain and changes in surface roughness, and it retains the observed track. So let me show an example here. So this is from Maria in 2017 over Puerto Rico. So on the left is step 1 of our modeling approach. So this is a wind swath of Maria using, I think it was the Willoughby parametric wind field. So this is the wind field equivalent to the winds at 2 kilometers above the surface in the absence of surface friction. So you can see it's a fairly smooth wind swath across the island. And then step 2 is we use the wind field on the left to drive on numerical boundary layer model. And you can see it brings a lot richer texture to the surface winds. So we get immediate breaking of the winds at the coast. We get reacceleration of the winds on up windward slopes and over crests of mountains. We get deceleration over the rough surface of urban areas, and then a reacceleration of winds as the cyclone exits the north side of the island. And just to show that this is a time evolving model, here's a quick movie loop of our model applied to Hurricane Michael in 2018. So this was the storm that intensified as it made landfall in the Florida Panhandle. And it even took Category 3 winds there into Georgia, one state inland. So obviously the wind's decaying now. There's some acceleration over the terrain in the southeast US, and the storm's getting wider now, and then the winds reaccelerate offshore again. So that was just to demonstrate that it's a model of the time evolving wind field, so we can pull out snapshots of interest. So let's go back to Otis then. So here is our model applied to Hurricane Otis. So the blue colors are the strongest winds. You remember it was 165 miles an hour at landfall according to National Hurricane Center, but now we've mapped the winds spatially. So the black line is the track, the colored circles are the recorded maximum wind speeds along the track, and the gray contours are elevation, I think every 400 meters. So you can see the strong winds really extend far inland, and I looked and we've got Category 4 winds 90 kilometers inland. And then we can quantify, how far along the coast the damaging winds extend, and get a sense for the complexity of the inland wind field. Okay, just before I go into that one. So this was the model applied to Otis, and we actually applied it to over 1,000 historical landfalling tropical cyclones globally. And with this data set, we can perform some statistics of how inland winds behave. So that's what I'm showing on this slide here. So this slide shows that coastal terrain can reaccelerate the surface winds, and to such an extent that they can even exceed the over ocean values. So let me tell you what you're looking at here. Along the x-axis is the inland distance along an average track over China and Taiwan. So we're looking at about 80 historical tracks averaged over Taiwan and China. And the dashed line is the average terrain heights experienced along the tracks. And so that's the right-hand side y-axis. So we can see there's a coastal mountain, and then it drops off to lower terrain behind, and this is probably the mountains of Taiwan. And then the black solid line is the distance rate of change of wind speed. So anything below the dashed dot line is a decaying storm. Anything above is an accelerating storm. So immediately after landfall, we have decay, as you might expect. but then because of these mountains, we have a reacceleration of the winds up the windward slopes that peaks at the crest of the mountain, and then we get our expected inland decay. So terrain really has an impact in the climatological sense of inland wind. Okay, so talking about some applications of this work, we can really use these footprints to understand historical losses. So here's an example of Hurricane Charley in 2004. So on the left is our wind footprint. Again, the black line is the track, and the colors are the storm lifetime maximum wind speeds. So you can see that the winds are really tightly confined to the right of track. Charley was a very small storm, made landfall as a Category 4. And on the right is a measure of losses. So this is a collection of insurance industry insured losses by zip code. And it's normalized, it's a loss ratio normalized by exposed insured value. And the redder the colors, the more intense the losses. And you can see that the losses are really tightly confined to the track. And that's because Charley was such a small storm, small in terms of spatial area. So we can do this exercise over many storms and look at the variations in storm footprints versus loss. And then we can also explore loss sensitivities to the hazard component. And so with WTW, we conducted a sensitivity to variations of Hurricane Irma that made landfall in Southeast Florida in 2017. So on the left is our control simulation of Irma. There's our footprint. And then in the middle, we increase the track wind speed by 10% and recalculated the surface wind footprint and ran that through a portfolio, and the losses almost doubled. So very nonlinear responsive loss to just a 10% increase in winds. And then on the right was another scenario where we just shifted the track of Irma, so it made landfall closer to the exposed value in Miami, and the losses increased almost 2.5 times. So it's a really flexible modeling system to explore sensitivities to events that could have happened but didn't. Okay, well, just to wrap up, I'd just like to advertise that was a wind footprint model, and we're now adding a rainfall module to it. So we're adding a published model in these papers here that is a simplified physics model that represents the 4 main processes that drive rainfall rates in hurricanes. So here's an example of a rain swath for Hurricane Eta in 2020 in Central America. And we see that the rain increases due to spin up of the vortex of intensification just prior to landfall there. And we also get enhanced rainfall due to convergence, frictional convergence as the storm made landfall, and also convergence due to the terrain of Central America. So the nice thing here is that the rainfall is physically consistent with our wind model, because the rain responds to the wind convergence during the hurricane track. Okay, well, I'll leave it there then. So yes, so just to summarize then, so we mapped the behavior of inland TC winds globally, and we did that using a new coupling of a parametric model to a numerical boundary line model that is terrain aware. And the results had made scientific advances and were also relevant to the insurance industry because of this collaboration as part of the Willis Research Network. So I'll leave it there. Thank you very much.
Okay, perfect. Thank you, James. Really interesting presentation, and certainly gives us something to think about how the models and the tools that we use within the industry take account for the terrain within them. So yeah, certainly something I'll be taking away to go and have a think about and look into. We have one question, kind of more maybe perhaps a comment. Oh, actually, there's another one coming through. Bear with. So Jonathan Lister has said, this is a little like huge variance in tidal behaviors. To what extent do you address fluid dynamics? Orlando et al.
Okay, I'd have to check that reference. In terms of fluid mechanics, yeah, the nice thing about this work is that we lock the hurricane along the observed track, and we only allow variations in winds below gradient, so-called gradient wind levels, so below 2 kilometers. So this allows wind speed up slopes and on crests. It has a memory as well, so upstream features know about downstream features and the effect on the wind. So in terms of fluid processes, that's what our model includes. Yeah.
Okay, perfect. Thank you. And one more is, if I understood correctly, is the global footprint data set of wind based on this new coupled model?
Yes, that's correct. So it's a data set of over 1,000 wind footprints, just like the maps I showed in the talk, and it's available on Figshare, and I included a link in the slides.
Okay, perfect. Thank you. We have just got one more, and then we'll probably have to move on then in the interest of time. So this one is from Michael Johnston. This is a really interesting approach. I might have missed this. Is there any accounting for whether wind is blowing onshore versus offshore, and validation against any surviving surface gust observations?
Yeah, good question. Yes, it does account for onshore versus offshore. If I scrutinize some of the maps I showed, I can see the strong winds extending a little bit onshore and then really dropping away. And then similarly, offshore winds, I see the slower winds reaccelerating offshore. So like I say, there's a bit of a memory in the wind flow in this modeling system. In terms of validation, in the paper, there's a validation against the observations that did survive hurricanes, but as we know, that's one of the big problems here, a lack of data. But the validation, I didn't validate onshore versus offshore specifically, but overall the model performed well.
Okay, perfect. Thank you, James. And with that, I'll pass over to Matt to introduce the next speaker.
Great. Thanks, Katie. Thanks, James. So we'll come to our third and final speaker now. So Sem is going to give another 15-minute presentation for us about using AI for global crop model forecasting. So yeah, take it away, Sem. Sem, you're on mute, I think, still, so we can't hear you at the moment.
First step, off mute. No. Okay, let's try this. I wonder. Do you see presentation?
Yeah, we can see the presenter mode at the moment with like the 2 blank screens.
Okay. Try again.
Perfect.
Great. Thanks also for having me. Yeah, I will have a slightly different story compared to the previous one. So I will focus on the added value of seasonal forecasting, and I hope people can find some links and relevance to the insurance sector as well. I tried my best to take this into account. So what I'm going to address today are these 3 questions. So how can AI or machine learning help forecast the weather months in advance? Why do we need these weather forecasts at longer lead times? And in the end, I will present some results about predicting yield later at long lead times, even before sowing. So first question, so how can AI help the weather forecast in a long range? So let's first address a bit the background story. Of course, we are dealing with climate change, which is increasing all kinds of weather effects like heat waves, droughts, and rainfall. And this is impacting various sectors. And I'm going to focus on agricultural and humanitarian aid impacts of climate change and how seasonal forecasts can help in that respect. So first, a bit of a background about this subdomain called subseasonal to seasonal weather predictions. So normally weather predictions, they are made for the short to medium range, and they can heavily rely on the atmospheric memory, basically the fluid dynamics in the atmosphere. And on the right-hand side, we have projections, and they are basically forced by CO2. But in the middle, we have this prediction desert. So predicting weather on these 2 weeks to seasons ahead timescales is quite difficult. So the short to medium range is tackled by the famous numerical models like ECMWF. And on the right-hand side, we have the climate models doing the projections. And of course, we now also have a new player, as many of you have heard, which is AI models, also on the short to medium range. Players like Google, Huawei, and NVIDIA are all playing this game, I would say. And so we are in the middle here. Just a short intro. I think I forgot this. Out of my PhD work, we wanted to really make something useful for society. So we decided to start a spin-off company called Beyond Weather. So you also know who we are if I say we. So a bit about the physics. The predictability of weather on weeks to month, weather on a long range is pretty difficult, and most predictability stems from these slow-moving components in the climate system, as I have kind of schematically illustrated in the right figure. And on the left-hand figure, you also see that the predictability on these timescales is less, and the predictability stems from mainly from the ocean and land dynamics, because these systems have a higher memory compared to the atmosphere. And then our challenge is with machine learning is to take the climate data in and learn the relationships between what we want to predict and the relevant slow-moving climate processes. And like a typical well-known example is, for example, ENSO, which influences weather in the US and South Africa, for example. So these type of processes, our model tries to learn automatically and optimize for them. And then when we've learned these processes, we can basically train an ML model and predict weather, try to predict weather months in advance. So we see that the unique selling points of this approach are that we can achieve higher accuracy for some regions and seasons. And another interesting thing is that our methodology has a high level of explainability, because we can actually visualize where the predictability is coming from, which is not something that can be done even with the numerical models. And lastly, we can assign confidence scores. So I will come back to this. I will come back to this. I think that's smart. So now the motivation, basically. So why do we need weather information so far in advance? And I first would like to illustrate it with a case that is very relevant for the humanitarian aid sector. So the Horn of Africa has been exposed to a lot of weather risk in the recent years. So in 2020 up to 2022, there was like a very persistent drought, and basically all of the rainy seasons failed in that period. And failing means then that there was less rain than that it was in the lower 33 percentile. And 4 million people were exposed to food insecurity because of that. And recently, the World Weather Attribution also analyzed that this event, this severe drought event, would not have occurred without climate change. And the physical mechanisms behind it could be traced back to the increased evaporation because of climate change, but also the climate dynamics are very important because there was a very persistent La Nina state, which is also known to affect this region. And recently, actually, this is sadly, the case that now the La Nina state has finally switched to like an El Nino state, but this then again caused floods, which is a typical thing you see, drought to flood mechanism that the soil cannot handle a lot of intense rain because it kind of captured anymore after being dry for such a long time. So humanitarian aid sectors or organizations, of course, want to tackle this problem and help these people. And therefore, they are setting up anticipatory action plans. And basically, this means that they are providing aid before disaster strikes. And this has numerous advantages, such as reducing human suffering, reduce the impact of the climate disaster, and also it can be, if it's implemented correctly, more cost effective. But these mechanisms, they require to have the information at a sufficient lead time. So they need time to prepare. And one of the main reasons why there is still a limited adoption of these type of anticipatory action plans is because of the lack of effective climate and weather forecasts. So there's a clear need for these weather forecasts at longer lead times at least for the humanitarian sector, definitely. And then from a farmer perspective, this is also very relevant. So I show here the typical growing season of soybeans in the US, which roughly, it's harvested roughly in October, and it starts, they start sowing in roughly May. But these soy plants are particularly sensitive to combined hot and dry weather in the July, August, September months. And they can actually take very effective measures against these hot and dry extremes. And for example, by reducing plant density or buying drought-resistant seeds or avoid planting the drought-prone areas, or for example, insurance. But this information is basically not yet there. As the first conventional USDA outlook is released in August. So this, and then of course the soy seeds are already in the ground, and the farmers cannot take these type of decisions anymore. Another case for arguing that we need these type of forecasts is that these you have certain crops which are quite localized, and localized, I say in quotation marks, because of course it's a large region, but still most of the production of soybeans, for example, occurs in the Americas. So either Eastern US, as you see on the plot, or South America. And this actually introduces quite a sensitivity, because if in both these regions the crop fails at the same time, then this can lead to huge price spikes and increases in food prices. And common climate drivers is actually a very important aspect in it. So a colleague of mine actually investigated this, and he found that the persistent La Nina states increase the risk for these simultaneous yield failures, and these can really lead to price spikes. So if we now look at two cases where this actually happened, we see here the soybean prices during the period of 2010 to 2014 and the period of 2020 to 2022. And both of these periods were characterized by a persistent La Nina state, and we see kind of a similar evolution in the soybean price and also this increase. So I would guess we want to protect ourselves against these type of unwanted impacts. So a question I addressed during my PhD was, can we predict yield impacts even before sowing in the US? So let's start with the important part, which is actually the physics behind it. So how can these climate processes lead to impacts months ahead? Well, I basically found that or using these machine learning techniques, I found that there is this horseshoe-shaped pattern in the North Pacific that increases the probability of these type of Rossby waves in summer. And you see here in red, you see this indicates that there is like a high pressure system occurring above the eastern US, which is exactly the region where a lot of the soy is being grown. So yeah, and this high pressure system then of course leads to less rain, higher temperatures, and particularly, as I said before, these hot and dry weather events, they can severely reduce end of year soy yield. So we tried translating that into a prediction, and luckily we were able to use this information from the ocean to make forecasts for yield events 8 months already prior to the harvesting moment in October. And this is really sufficient lead time also to help out farmers with taking anticipatory action. And yeah, so when this forecast was issued, there was like a doubling in probability of a poor yield year. And a poor yield year would be defined as the yield anomaly being in the lowest tercile. And yeah, we are now also looking into Brazil as well, and the US also, to also make predictions for temperature as well as soil moisture. And we are also achieving quite long lead times there. So this basically, yeah, gives additional reliability and additional information to the user. And an interesting aspect here, an important aspect, is this concept of windows of opportunity. I think many people in the S2S, seasonal weather prediction community, know about this topic. Is that because also, I think especially because it's a boundary forcing problem, then it basically means the skill you can expect really depends on the background state. And so more extreme state basically means a higher signal to noise ratio. And in those cases, you can then also expect a higher precision, higher accuracy. And we also confirm that for these crop forecasts. So some years are more predictable than other years. And being able to distinguish these more and less and more predictable years is, of course, valuable information. So to conclude with these 3 questions, how can AI help forecast weather on the long range? Well, it can help by extracting the relevant slow components and of course fitting the proper model, statistical model to it. And why we need it? Well, I hope to have convinced you that there are a variety of anticipatory actions that really require this long lead time and that can really save or mitigate a lot of weather risk. And then lastly, can we predict yield impacts even before sowing? And yes, we can for some regions. Yeah, so happy to have shared that. And if there are any questions, happy to answer.
Great, thanks, Sam. That was super interesting. So just to kick things off, I've got a question, if that's all right. So you talked about obviously how your AI models are trained on the historical climate and the forcings that we see from things like ENSA. If you wanted to apply this model, say, for future climate, as we go on with climate change, and say the interaction between large-scale modes of variability changes, will this mean that your AI model will become less reliable, or would you just simply have to kind of retrain it?
Yeah, excellent question. I think there's a lot of research being done into, like, do these interactions also change with climate change, and to what extent is there decadal variability acting? So these are very difficult questions to address because of the limited amount of data. So I would say it's very good to investigate this before you start applying such a model way into the future.
Great. And we've got a few more questions coming up in the Q&A as well. So one from Christopher Allen. He's asking that, so for the people who are more familiar with NWP, could you give a bit more of a background as to how these AI models work? Do they use the physical equations that govern atmospheric motion? And what do you mean by the models learn slow-moving climate processes?
Okay, that's an excellent question. Maybe I will start sharing again. Yeah, maybe I should have added like a clearer picture again. But for example, the learned slow components in our case means that it has identified this region, and it's basically using this, it reduces this feature to one-dimensional time series, and we do this for ocean temperature as well as soil moisture. So we find these important regions, reduce them to single column time series, and then we can basically fit a statistical model to it. So that's how we find these slow components, and we can also trace back and show kind of, okay, this was the region and this is the importance it was given. And more general, maybe to step a bit back and say like the comparison between NWP and AI models, like our model really tries to focus on solving this boundary forcing problem. So this problem for the sub-seasonal to seasonal timescales. But if you look at, for example, what Google and NVIDIA, also ECWF, are doing with this new generation of AI models, then it's more, they don't learn the equations of motions, but they map basically, given this state of all my variables, like geopotential height and well, all kinds of pressure levels. They have information about the wind, etc. Like what is the most probable next step in the next hour, so to say. So they basically used sequence to sequence mapping of kind of 3D images to make their predictions. So these are two fundamentally different problems and also different methodologies.
Great, thank you. And then just one more that we have as well here from Ruth Petrie. So Ruth's asking that in insurance, they normally write contracts for the following year. So what do you think the limit of predictive skill would be as AI use develops? And do you think it's dependent on peril and region of the world?
The second two questions, definitely yes. It matters a lot in which region you are. So the US, the Americas both are heavily influenced by the ocean temperatures in the Pacific, the dynamics in the Pacific Ocean. And of course, in Europe, we don't have the strong link to the Atlantic, and also we're further away from the Pacific. So there's less predictability. We also see that in our results. And about the maximum lead time, well, like we got back up to 8 months in advance for these soy yield fluctuations, and it was still quite reliable. And we actually didn't test if we could extend this further back. We were already quite happy, like with 3 months before sowing, we were like, okay, our job's finished. But yeah, we will continue to do experiments at longer lead times with this spin-off company, Beyond Weather.
Okay, great. Thank you, Sam. I suppose for the interest of time, we'll leave that there. I'm aware there are more questions in the Q&A, but if we have time in the open discussion, we can come back to some of the ones that we have there. So what I'd like to do now is kind of like invite the three speakers back in. Great. So yeah, for the next 15 minutes or so, we have a chance to kind of ask some more general questions for the speakers here and kind of have more of an open discussion. And I suppose just to kick things off, something that I wanted to ask you, so you've all kind of presented different methodologies here, use different data sets and different ways of tackling problems. So I suppose the general question is something that we deal with quite often is how do you deal with, or how much of an impact are these uncertainties in your work that's arising from things like different data sets or methodologies or variables that you're using? For example, Sandra, you talked about different SSI metrics that can be used or different seasonal forecasting products. I just wondered if the three of you could comment on that at all as to how you deal with those sorts of problems in your research.
Yeah, since you mentioned me, I'm happy to start. So I think, yeah, there's definitely uncertainties in the approach. The model that we use will obviously have limitations and biases. And as I mentioned, the corrections we do, because it's based on wind speed data, not gust, and having to correct that and adapt the SSIs, that introduces some error. It would be interesting to look at it on a finer resolution than just country level, maybe, to see if we can capture some more local features. But I think one of the ways we've tackled it is from subsampling from the event set, so trying to get a range of outcomes for that event set that we have, but also just looking at as many different data sets as we can, looking at different studies and trying to get sort of a general view on what's out there in terms of the metrics that we look at.
I suppose on that front as well, with regards to, like you said, about different data sets, things like, so you use the glossy data in your work. If you used a different seasonal forecasting product and it gave you a different answer or different events that were structured differently, would that affect your line of work at all? How would you decide kind of if there was a correct one, or would you use all the information you have to kind of come to the best overall outcome for your needs?
I think we'd look at all of them and we'd try and sort of qualitatively address the limitations of each approach. And I think we're not trying to get an exact answer here on what is the SSI value of a 200-year return period storm. It's more in terms of trying to understand the uncertainty in it and the, just trying to find more data sources, because at the end of the day, a CAP model it has its own limitations, and there's just not, we don't have observational data that goes back 200 years. So yeah, so I've forgotten what your question was. Yeah, I think we would just qualitatively try and assess the benefits of each, and it would affect our outcome, but we don't use just one model, one answer. It's more about understanding the uncertainty.
Great. And James, do you have any comments on this area?
Yeah, so in the project I just talked about, my hurricane wind model uses track data as input. So really, I really want high quality track data, and that can be problematic if you're looking globally. Only a few storms have, aircraft reconnaissance that gives a reasonable estimate of the peak winds, but then again, it's not recorded where those peak winds are. There's rarely information on asymmetries, and it's even harder to get accurate information on size, so radii of different wind thresholds, which is important because I'm fitting that parametric wind field model to that information. So there's a huge amount of uncertainty. It would be nice if I could run some ensemble simulations of each storm that samples that uncertainty in the input data, to get a better spread and better understanding. I have another comment on uncertainty. Just thinking generally about perils in the changing climate. I think it's important to understand the scales that you're interested in, because the importance of uncertainty from different sources varies dramatically with the scale you're looking at. So we can discuss that as well.
Great, thank you. And Sem, do you have any comments on the area of uncertainties and handling that in your work?
Not really. More data, always welcome. Higher reliability, always welcome, of course.
Great, thank you. Did you have anything, Katie?
Yeah, I've got a question. Oh, excuse me. So I wondered whether each of the speakers today could just comment on what they think are the key questions surrounding weather and climate hazards that are the most important to answer within the next 5 years. I know it's quite a open question. Sandra, I don't suppose if you want to go first again.
Yeah, sure. I mean, for me, I think it's understanding the relationship between all the different atmospheric conditions. So I was thinking about kind of the Italian hail events of this year, which caused huge market losses. And I think of around 2 or 3 billion euros. And the conditions for that event were, there was record-breaking temperatures in the Mediterranean. There was, repeated low pressure systems bringing in moist air. There was a lot of instability. I think it was blocking. It made it sustained for several days. And each of those components perhaps are not that unusual, but altogether it seems to be an unusual event, and it's not well captured in CAT models. So sort of my question is, what we want to try and understand is how often can we expect these events to happen? And in order to understand that, do we really understand how all these atmospheric conditions react together, but also how they're going to change in a future climate? I know the climate models, you know, they are quite sophisticated, but I'm not sure if they capture on that scale the likelihood of these sorts of conditions occurring together and creating these really severe events. So for me, it's around understanding current and future climate and how all these conditions interact to create these extreme perils, and also the correlation between these perils. Can we expect years with extreme hail? Will that occur at the same time as extreme flooding, or is there some kind of anti-correlation or whatever?
Yeah, I see. And I suppose it kind of ties in a little bit around like cascading events, or perhaps even cascading conditions with something's a little bit different or has changed. Has it, what's the like knock-on effect then potentially on events, and then therefore the losses, of course. Fabulous, thank you. Okay, James, I suppose if you want to go next.
Yeah, so I mean, there's lots of exciting questions. What I'm most excited about is the dawn of kilometer scale climate modeling. So this is running climate simulations at a scale that can resolve Category 5 hurricanes and mesoscale convective systems and severe cold fronts associated with atmospheric rivers, for example. And this allows us to understand a lot more about the processes that drives extremes. So one of the big questions is the role of land surface coupling on, say, extreme precipitation. We haven't looked at that on climate timescales and how those feedbacks interact in a changing climate. That's a big unknown. Another one is the role of these fine scales in climate that upscale and maybe impact things like El Nino and other longer term modes of climate variability. So we know very little about that, and we're only just starting to get the tools to explore that. Maybe I could say on a practical level, one of the big challenges we all face is how do we connect climate change information with CAT modeling? So there's lots of people are doing this, doing it in different ways. I might suggest it's not very coordinated. So I think the field's wide open to understand how to do this in a physically consistent manner.
Okay, perfect. Thank you, James. I think that might be a good segue into something that Matt's going to talk about at the end. Perhaps an event we've got coming up a bit later on, but I won't do any more spoilers than that. Sam, I don't know if you got anything you'd like to add on what you think is a key question that needs to be answered in the next 5 years.
Well, what I find, of course, very intriguing is the AI revolution, I can say. I think that is going on in the weather forecasting community. And I mean, I think it's also very fair to then ask, okay, what are we missing in the NWP, the numerical models? Because apparently it is possible to get this predictability. So I hope we can also learn and like iterate between the two methods.
Yeah, absolutely. Okay, perfect. Thank you. So we've still got some time. Matt, I don't know if you wanted to look back on some of the questions we've got unanswered, or if you want to dive into.
Yeah, sure. We've got a few minutes, so we can, I suppose, get into some other questions. So thanks to those that have put some more questions in the Q&A. A couple of questions linking back to your talk earlier, Sam. So Bruno Costa asked what the main advantage was of using the machine learning technique over dynamical seasonal model outputs like things from the ECMWF. I know you touched on this briefly, but if you could kind of say a little bit more about that, that would be great.
Yeah, of course. So I think the main problem with seasonal models from the numerical models are that they are not very reliable beyond even week 3, 4. It starts to diminish rapidly, and 1 month in advance, it gets very tricky. So lack of accuracy is a problem, yeah, that needs to be solved if you want to make these forecasts actionable for stakeholders. And yeah, I hope, of course, that with the AI, we can push this further. And in some regions, seasons, we can. For example, I mentioned already, Europe is quite difficult. We are getting some promising results there, but still, I wonder, yeah, what else we could achieve. So accuracy is definitely one of the things. Explainability, I think, is also quite a nice feature that even it's a bit of unexpected, but these machine learning techniques can definitely help with explainability in a new way compared to NWP models.
Great, thank you very much. Yeah, I'm aware that obviously it's a very new and upcoming field, so obviously developments are really rapid. Someone else has asked Sandra if you could just say a bit more about the unseen approach for those that aren't familiar with it.
Yeah, for sure. Let me share a slide that might help a bit. I mean, it's basically using a model data to provide additional information. Sorry, I can't do a slideshow right now. Yeah, so I mean, there's a paper by Thompson from 2017 about this, but it stands for unprecedented simulated extremes using ensembles, and it's using a model to provide a larger sample of plausible events. So it's not a statistical event set, but it's based on a physical model.
Great, thank you. And so we've got a question here for you, James, as well, from Morteza Musa Vizadeh. Sorry about the pronunciation. And they just wanted to know about predicting tropical cyclones using AI and machine learning methods, such as what Sam talks about. Is there any research ongoing on this at the moment that you're aware of?
Yes, yeah, these identification and tracking routines exist. So people have machine learned TC detection algorithms in model data. And also other phenomena, like there was a recent paper on detecting fronts, cold fronts, warm fronts using machine learning, and there's one on atmospheric rivers. So yeah, very fast-moving, evolving field.
Yeah, like you say, as I'm sure as these AI and machine learning models become more and more developed and advanced, it's only something that we can use more and more in the future, things like this. And then I suppose a final question addressed to anyone is that when you talk about generating vulnerability curves to your different hazards and perils, how much of a challenge is this? And are there any AI methods that are being done to do this, or is it purely from dynamical models?
I mean, I can comment. What we tend to do is it tends to be based on claims data or engineering studies. So rather than, yeah, it's not, I suppose physical engineering models can be used to come up with vulnerability, but they're always, we always try and calibrate them or at least validate them against some claims data. I haven't really thought about how to use AI in that respect. I mean, I'm sure AI can be used for practically anything with sufficient data. But I mean, this is one of the major problems we face as an industry is the lack of data, and then also the sharing of that data. Not everyone has access to it.
James or Sam, did either of you want to comment on that at all?
I'm actually collaborating with engineers who go out into the field after a hurricane and study the structural damage to buildings, and then we're correlating that with some of my wind field data to understand some of these curves. So that's how my work's involved in vulnerability.
And Sam, do you have any comments on that finally?
Excellent.
Okay, great. Well, seeing as we're nearly at the end, I'd just like to take a quick opportunity to thank all the three speakers again for their presentations, their interesting discussions. It's been really, really great and really insightful for a lot of it. So yeah, thank you so much for sharing your time. And one final thing I'd like to bring to everyone's attention is that if you found the presentations that we have had here interesting and discussion insightful, the Insurance Special Interest Group is hosting an event in London in January on navigating climate challenges in insurance, where we're going to get people together to discuss the exact things we've talked about here, how we can do research in insurance more practically, what the big questions are that need to be answered in the next 5 years and how we might go about approaching them. So if you're interested, you can follow this link here, or go through the Royal Met Society events page where you can register. Registration is up until the 5th of January for initial expressions of interest. So please do so if you'd like to contribute to these sorts of conversations more. And finally, just one thing to highlight as well, that this event hosted by the Royal Meteorological Society has been a way of bringing this research to yourselves. And if you are a member, thank you. And if you're interested in becoming a member, please do consider it. There's a lot of great benefits, such as the masterclasses that RMETs run every year, webinars such as this one, and also for the events and conferences that are hosted. There's special rates for the members and access to some of the online journals as well. So if you're interested, go to rmets.org/membership. And if you want to hear more about what the insurance special interest group is putting on in the future as well, the link at the bottom, the insurance page at RMETS, you can sign up to the mailing list that we have there for future events that we have, such as this in the moving forward. But with that, I'd like to bring it all to a close. Thank you to James, Sandra, Sem, and Katie for presenting your work and discussing today. It's been really insightful. Hopefully everyone else has found it really interesting and has things to take away with them. So yeah, thank you very much for spending your time, everyone. And please look out for everything we have going on in the future. Thank you.
Yeah, I'd just like to say thank you to you, Matt, as well, for hosting the event.
Thanks, Katie.
Thank you. Bye-bye.
Cheers, everyone.